Hello. Uh, in this lecture, we are going to review the programming concepts, cryptographic hash function, RSA, encryption, decryption algorithms, elliptical curve, digital signature. And in the meantime, I'm trying to solve the questions from midterm examination. So let's start. At first, I'm trying to start with cryptographic hash functions. Okay, as I said, there are two different libraries in Python for implementing and using different hashing algorithms. One is hashlib. Another one, which I think is it's a more general library, is cryptographic hazmat primitives. Okay, it doesn't matter which one you are using, because the algorithms are the same. For example, SHA-1 here and here, both are the same. So if you want to hash some information, at first you must import the library, then you must create an object by this command, hashlib dot. The name of the algorithm here is SHA-1. You can use, for example, SHA-256. So M will be a hashing object. Then, using this command, update, you put the information you want to hash. For example, here it's my name. But by putting a B before this string, I'm converting this string to a byte type. Okay, so here I have a type conversion. Then simply I can print the output. If I run the program, okay, this is the output hash of my name using SHA-256. I can change it to SHA-1. Again, if I run this, I have the output using SHA-1. I also can generate the output in different steps. For example, in the first step, I just put my name here. In the second, so in the first step, I just put my name. In the second step, I concatenate to my name, my family, and again here I can, as you can see, the output is the same. Okay. I can do this in another way. You can change the type of this output of hashing from hexadecimal to byte by this command. This is hexadecimal. As you can see, this is the output of hash my name. By this command, bytes from hex, you can convert a hexadecimal to byte. Let's run it. As you can see, this part is exactly as the same as this output, but this output, this highlighted output, is in hexadecimal format, but this one is in the byte format. Okay, If you want to use this library, okay, for defining an object, we use this command, hashes dot hash, hashes dot the name of the algorithm, SHA-256, or you can use SHA-1. Then again, using update command, you can put all the information you want to generate their hashes. At the end, you must use finalize command to close the hash. Please note, while you are using this library, you don't need to use finalize, but if you are using this library, you should use finalize before printing the output. If I run this, as you can see, the output from two parts is the same. As you can see here and here, this is the hash of my name, and let me copy, paste. If I run again, as you can see, if you print digest directly, the hash of my name will be printed, but in the byte format. It's a byte format, okay? This command converts the byte format to hexadecimal format, so this is the hexadecimal format. This is the hash of my name in hexadecimal format. Again, using this command, you can convert the hexadecimal to byte. As you can see, this part is exactly the same as this part. It means that when you print digest, the output is the same as when you convert this hexadecimal to byte. Both are the same. Okay? So here there are different examples that you can use different SHA algorithms. You can put different information in each part, and that's it. So this is hashing. Okay? What's the difference? The main difference is that the length of the output. For example, when you use SHA-1, the output is 160 bits. In hexadecimal, it is 40 letters. If you count the number of letters in this output, it should be exactly 40. But when you are using, for example, SHA-256, the output, the length of the output will be 256 bits. In hexadecimal, you should divide it by 4. It means that I think 64 letters. So if you count the number of letters in this output, it should be 64 letters. Okay, this is the as you know, the cryptographic hash functions. For each input, you will have a different output. This is cryptographic hash function. It's a one-way function. It means that using the input, you can find the output, but having output, it's not possible finding the input. Okay? From my name, by the hashing algorithm, we can find the output, but just using the output and the algorithm, the name of the algorithm, it's not possible to find the input. Okay? This is hashing, cryptographic hashing. Let me check the questions. We didn't any question about hashing, I think. Yeah, this question. In the second midterm, in the second exam, you were asked to using the following hash algorithms: hash your name and copy paste the result in the answer box. SHA-1, SHA-256, and SHA. Simply you can use this program. For example, this is my name and this is the output of SHA-256. You can change it to 512, run it again, and this is the output. Okay, so let's move to RSA encryption decryption algorithms. As you know, RSA is one of the algorithms which is used for encryption and decryption, and also we can use it to create digital signatures. Okay, if you want to run these programs, if you want to use the RSA algorithm, you should use these libraries. Okay, RSA serialization and default backend. So in the first part, we should generate private keys and public keys. To generate private key, using a command like this, rsa.generate private key, with these parameters, we can simply generate a private key. So private key now is a private key generated by RSA algorithm. To print it out, you should serialize it. To serialize, you use the private key, again the command private byte. You can use two formats for the output, PEM and DER. PEM is something like this, starting with these words, begin RSA private key. But DER is a byte format. If I change it to DER, so this is DER, a private key in DER format. Okay. Oh, sorry. This is the DER format. It's a converted to byte. So usually PEM is more comfortable for people. Okay. Now to generate public keys, simply we use this command, private key dot public key. So this is public key. Again, you can print out the public key, but also you can open a file and save the private key inside a file. This is the private key and this is the public key. Okay. So in the first midterm, this is the second, the first term here, question 1, part A. Using RSA, generate a private key and a public key. Send the generated keys as a text file. So you could simply run this program and copy paste these two parts onto your answer sheet. Okay. Please note this part save the private key inside the file with this name. You can change the name whatever you want, and this part of codes save the public key inside the file with this name. Again, you can change the name of the file with everything you want. So in this code, not only we have generated a private key and a public key, but also we have printed them out, and also we have saved them, both private keys, both private key and public key inside the file. Bob private key.pm is the name of the file containing the private key, and Bob public key.pm is the file name containing the public key. Okay, so this was the answer of the part A. Okay, let's continue. But this part now, I want to encrypt some information using RSA. To do so, here we have a plain text message. Whatever you want to yes, this session is recording. Yeah, the recording is active. Here you should put everything you want to encrypt. For example, I want to encrypt my name, so I put my name here. Then I load my private key from a file. Sorry, for encryption we need the public key. Here I have loaded the public key from a file. This file was created here. This is the file. In this part, I saved the public key and private key in these files, and now here, using this command, load PEM public key, okay, I read the public key from that file, from this file. Then, using this command, what is Alice public key is here. Alice public key dot encrypt, this command, with these parameters, I encrypt the message. Ciphertext contains the encrypted message. Plain text message is exactly this message. In the question, you were asked to use your name, so this is my name here, and this command printed out this ciphertext. So if I run, this is the encryption of my name using that public key. So let's check the question again. In part B, you were asked to encrypt your name and family using the generated private key in part A. Send the encrypted message as a text, not a picture. For example, I should encrypt this message. Okay. So this is the encryption part, and for the decryption, you can use this part. No. For the encryption, we use this part. Again, I should open the private key file. So sorry, this is the digital signature part. Let me find the yes, this is the encryption part. Here we should open the file containing the private key. Okay, as you can see, Alice private key will be the private key. Now, what is this? This is the encrypted message. Now I have the encrypted message here, so I copy and I paste it here. Okay, and now if I decrypt it, you can see the original message, which was my name. So that was the encryption. This is the decryption. And let's talk about the creating digital signature using RSA. Digital signature. let me this is the digital signature. You have a message here. You want to sign it, I think, in the second examination. No. What was it in the first? Yes, you were asked to create a digital signature, but using EC. So I will explain this question in the EC part. Okay. So let's back. Creating digital signature using RSA. You have a message here. This part, again from the file containing the private key. I load the private key. So Alice private key, this variable now contains my private key. This is the message I want generate the digital signature using this message. Okay, to create signature, this is my variable. I use this command. As you can see, this message is this. I want to create digital signature based on this message. Other parts always are the same. We don't change any part. And finally, here I have printed out the signature. And this is the signature. And now, how can I verify the digital signature? Simply, I copy the digital signature here. I put it here. In fact, I should convert it to byte format using bytes from hex command, using this command. So this is the signature created here in byte format. This is our message. Ali, I, Wahid, give you $2. This is exactly, I want to check that this signature is exactly for this message or not. I want to verify that. To verify, you should use the public key. So public key is equal to Alice private key public key. This is the public key. So using public key dot verify, I verify this signature and this message. These parameters always are the same. Okay, I run it. There is no output, so everything is okay. But if I change a bit, for example, if I delete only one dot from the original message, and now if I verify the signature, you see the invalid signature message, because this message is not as the same as the original message which based on the digital signature was created. If I put the dot again and I run, everything is okay now. And this is the digital signature. Digital signature prevents others to change the original message. You have a message. Before sharing with others, you create its digital signature. So if others change the message by verifying the digital signatures, you can easily find that it's not the original message. Okay, and this was the RSA private key, public key, encryption, decryption, and digital signature creation and verification. So now I think in the first examination now, simply you can solve the first question. And the second and the third and the last part is elliptical curve. Okay, again we need some libraries. Okay, we have some functions here. This function simply takes a public key and returns its calculated SHA-1 hash. We know that addresses in different cryptocurrencies are hash of the public keys. This file, this function saves a private key in PEM format to a file name. Okay? Load key, this function loads a private key from a file. So, in this question, you were asked, suppose data is equal to your name. This is your name, data is your name. Now using the following private key and ECL to generate its digital signature. At first, the first step is I should save it to a file. Beside my other files. Exam key.pem, for example. I paste the key here. I save it. Exam _key.pem, and now by calling this function I can load my private key. Okay, to generate a private key you can simply call this function ec.generatePrivateKey, returns a private key. Then PM is the private key in the PM format, so you can print it out. So if I run it, this is my private key. To create the public key from private key, simply use this command, a variable, then then private key.public key. You can generate a private key. As you can see here, after printing out the private key, I have saved that key inside a file name alireza _private _key.pem. Save key. This is save key. Okay. Then here I have serialized the public key. This is PEM format. This is DER format. This is printing out the private key, and here I have converted the public key in DER format to byte format. And here I have converted the DER format address to DER format public key to an address. Okay. Till now I can answer this part. Which of the following transactions are not valid? Why? This is the structure of transactions. It was a very simple question, because this is sender hash. The first parameter is sender hash. The third parameter is sender public key. In the previous lectures, I emphasized that there is a relation between sender public key and sender addresses, wallet addresses. Who knows what's the relation between public key and wallet addresses? I will use. Don't worry, I will use. But answer me. What's the relation between public key and wallet address. Yes, that's right. Hash of the public key is address. If you know this, so you can simply solve this question, because this is sender hash, okay, and this is the public key. If you check the all transactions, sender public key is the same. You know, sender public key for all three transactions are the same. Okay, how is it possible to hash this public key but having different addresses? See here, this compare this address with this address with this address. Definitely at most one of them can be right. Now I want to check that is the sender hash is generated from sender public key. Now I will upload the public key. This is the public key, okay. This is the public key. I copy the public key. I'm here. Using this command, I convert the public key, paste, using this command, just this command, okay, just this command. Ignore the previous commands. Here I have converted this public key to a DER format, and after that, using calculate show on hash pop DER is this. I generate its associated address and then I printed out the address. So if I run this program, this is the answer. This part. Ignore this part. Ignore this part. Just this. So I copy. Here. This is the answer. So check all the three transactions. Which one has such an address? A9A. Let me check. No. And no. That's it. All three transactions are invalid. Yeah. But what if, for example, let me copy and paste it here, for example. Okay. Now, how can I verify this transaction? For the exam, that was enough. You could simply say the sender public key and its hash are not consistent, so all the transactions are invalid, and that's it. Okay. And now, what about the first transaction? I have checked the sender public key. I have generated its hash, and the generated hash is equal with this hash. What should I do? I should check other information. What information I can check? Now, nonce is not important here. I will explain why. This is the digital signature. Okay. The digital signature is calculated in this question. We don't have information for the digital signature because here you don't need it. Just this question, you could simply solve this question using these two fields. Okay, but for the second one here, I gave you the structure of the digital signature, I think. No. I think digital signature in the transactions, let me check. Signatures, digital signatures are created based on recipient hash, amount, fee, and nouns. So we can simply calculate digital signature by copy and pasting the information here. Recipient hash, recipient hash, this is recipient hash. Okay, I will put it here. Amount 7, so I will put 7 here. Then fee is 4, so I put 4 here. And finally nouns, so I put nouns is 1, so I put 1 here. D is the data which we should sign. Okay, if I run this part, this is digital signature, and now I should verify it using this command. But before that I should load the public key. This is the command that I use to load the public key, so I simply put it here. Now pop DER. Okay, verify. SIG, this is SIG. D, what is D? D, this is data, our data. Let me to run. Okay, byte object has no attribute here, so sorry, let me public key verify. Public key, so load. I should serialize it to a DER format. Let me to convert it to DER format. Coding DER, and pop DER byte. This is byte. Without private key load data, I give signature verified signature bytes from hex. Public key verify. Where is the public key? Public key, private key using. Since we don't have the public key, I think we can't verify the signature. Let me check. Name error. Data is not defined. What's data? Data. No. Here. D calculate signature. It's okay. Sign private key sign. So using a private key. To be honest, we don't have the private key, so you cannot verify the digital signature. You know, if you want to check it, you should have the private key. So in this question, okay, so in this question, we cannot check the digital signature because here we need the private key. In this question, you don't have the private key. So the only thing that we can check is that we hash all these fields, this, and all these fields, and check the output should be this transaction ID. As you know, the transaction ID is the hash of all the fields. So it means that we should use this command. We should use this function, something like this. I should put the information here. For example, I should copy this, put it here, then put other fields there, and then run this part. The output is, this output should be as the same as this one. If it's not the same, it means that the transaction is not valid. Okay, for checking the signature, we need a private key. Since in this question we don't have private key, so we cannot check the signature. But just we can check two things. One, checking sender public key and the sender hash must be consistent, as I checked. And finally, I can generate the hash of all the fields and then check that the output of the hash is the same as transaction ID. If it's not, okay, if it's not, it means that the transaction is not valid. But at least in the examination, you can simply check the sender public key and sender hash, because in all the transactions we have used just one public key, and one public key, it's not possible to have three different hashes. So in these transactions, at most one could be true, but as you can see, all three was invalid. All three were invalid. Okay, now let me to solve this part. No, sorry. This question. I want to generate a digital ask your question. Yes, we have. We have. All the codes are here. This is a code for saving public key, or this is a code for saving public key. This is a code for loading the private key. If you can save a private key and load a private key, then using this simple command here, you can see I have saved the private key. Then using this simple command, you can calculate its public key. So we have the code for saving the keys. Or for the public key, you can rewrite this function. Okay. Instead of private key, simply write public key. And that's it. Execute what? Which question do you mean? Now I'm trying to solve this question. I want to solve this question. Here there is a private key, okay? As I explained, I saved it in exam_key.pm, and now using by calling this function, file name, the name of the file name, exam key.pem. Okay. So now private exam key is my private key. The question asked, so suppose data is your name. Now create the digital signature. Okay. For creating digital signature using I should use this command. Okay, so I'll copy this, I paste it here. D is my data, so D is be my name as the question asks, and that's it. This is the digital signature, this is the output. Okay, so this is the answer. This is the answer of this question. Okay, so 1, 2, 3, all 3 questions were answered, and finally the last question in a transaction like the previous question was the application of nouns. As you know, we use nouns to distinguish between transactions with the same recipient and sender. When the sender and the recipient and all the data like the amount, fee, everything is, all these information are the same, nouns is used to distinguish between them, because I can consequently send, for example, 2 bitcoins to Alice 2 times, 3 times. How other nodes in the network can distinguish that all these transactions are the same or are different ones. About the second question, I think the programming part is only the last question. Using EC at first generate a public and private key, okay? Send them in the answer box as text messages. Then suppose the signature of a transaction includes the following fields: recipient address, amount, fee, nouns. If recipient address, amount, and nouns, using the generated EC keys, calculate the signature for this transaction. Okay, it's very simple because you use this function. Now, in this question, at first you were asked to generate public and private keys. So I have this part, the first part, okay? This is my private key, this is my public key. So I can simply use this function to calculate the digital signature. How? By copying this information, copy, paste it here. Then amount is 100, so amount is 100. Then fee is 0 and nouns is 1. Fee is 0, nouns is 1. It's okay. So I think it's enough. And that's it. This is the output. Okay, this is the digital signature. This is the digital signature. This is the answer of this question. And that's it. Okay. You were asked, can you run one transaction to send Bitcoin? The answer is it's not possible with this part of code, because when you want to send transactions, you need all the network. Okay? All these examples here, all these examples have created by hand. Understand? All these information were created by hand. If I want to really send a transaction, I should have all the codes. I should use all the networks. And we didn't talk about the network. Okay? So it doesn't mean I can create different transactions by hand, but not by code. You know? I can create separately a sender hash, recipient hash, public key. I can consider, for example, some amount, fee, nouns, and then I can create by the code the digital signatures, and finally I can create the transaction ID. But I haven't any code, or at least I didn't give you any code to generate transactions automatically. Okay? So you can't generate transactions automatically. You should generate them by hand. I think all the necessary codes, how to load keys. This is save key. This is load key. Everything can be found in this codes. Also, for the RSA, the necessary codes to save the keys, to load the keys, also can be found here. As you can see, using this command, you can simply save a private key. Using this one, you can simply save a public key. And then using this command, you can simply load a public key or using these commands to write and load public key and load private key. This is load public key, but we have load p and private key also. So you can use these two libraries to load private key and public keys in RSA. But in EC, we have these two functions. Again, load pen private key, load dr private key, load pm private key, load dr 2 times. We need them 2 times, just one is enough. Using these commands, you can save and load private keys, then using the private key and this command, you can simply generate the public key based on the private key. Okay? Oh, by the way, the last coding part was the mining part, not for the midterm, but maybe you have some questions in the final examinations. As you can see, we set a difficulty here, for example, 500. Based on that, a target is calculated. We have some information here. And now we want to find a nouns, putting at this information, at the end of this information, the resulting hash must be started with some 0. The number of 0 depends on the difficulty and the target. For example, here the output starts with 3 zeros. If you increase the difficulty, definitely the number of 0 will be increased. If you want to create a transaction, I'm answering you. If you want to create a transaction by which sending some Bitcoin, for example, to Bob, you need only Bob wallet address. You don't need Bob public key. Okay, so you should put your address, Bob address, your public key, amount, fee, nouns. Then you should calculate the signature and put the signature, and finally you should calculate the transaction ID and put the transaction ID, and by all these information you have a transaction. Okay? In fact, here as you can see, we just need the recipient hash, recipient address. But for the sender, we need the sender hash and sender public key. Because why we need the sender public key? Because other nodes can check that the sender hash is associated with this public key, so nobody can change the public key. Because if we can change the public key, so it means that the digital signature also can be changed. Okay, to prevent others to tamper the transaction, sender public key is considered inside the transactions, but for the recipient only the hash, only the valid address. Okay, so I think all the in the final exam, for example, maybe I give some information to you, and then I ask you to find a hash based on to find the nouns that if I put the nouns at the end of this information, the resulting hash starts with, for example, 5 zeros. Okay, so to do so, you can increase the difficulty. This is again 4, I want 5, so let me, okay. Now as you can see, the output, this is again 4, the nouns is 24, 31, 81. No, this is not my answer. I'm trying to calculate, I'm trying to find the nouns when putting these nouns at the end this information. The resulting hash starts with 50, and this is only 40, so maybe it's better to, I don't know, 8. Now I think if my computer can calculate the output, I think the resulting hash should be started with 50 bit, because the number of bits, yes, the number of bits is now 19. This is the number of bits. You know, this is hexadecimal, so every 4 bit is represented using 1 character. So it's nearly 20 bits. 20 bits means that we have 50. So the 5 leading zeros in this example. And so in the question you can say, okay, this is the answer. This is the nouns. If you put these nouns at the end of this information, and then if you hash the information with these nouns, the resulting hash will be started with 5 zeros. Okay. Let's talk about other questions. I don't know. Suppose you are in a reliable environment. In the environment, everybody has a private and public key, and people know the public key of each other, but the private key is secret. Now you want to send your friend Ali a message. Everybody can watch your message. Explain how you can send your message in a way that only Ali can read it, and Ali can be sure that the sender is you and not others. Suppose, okay, if you can remember, when I started to explain the encryption, decryption, at first I talked about the concept of encryption and the concept of digital signature. Okay, if you encrypt a message by your private key, everybody can decrypt it because everybody has your private key. As you can remember, I said it's not encryption, it's the digital signature, and using this, people can be ensured that the message is received from you. So in this question, at first we should encrypt the message using the public key of Ali. So at first I encrypt the message using the public key of Ali, and then I encrypt again the resulted encrypted message with my private key. Okay, then I send it to the network. Everybody can decrypt it, but after decryption they have an encrypted message, and only Ali can decrypt that, because only Ali has the associated private key. But in the first step, everybody can check that it's me. Okay? So combination of digital signature and encryption is the answer of the first question. The second question, we know in each transaction there is a field named nouns. Suppose you are not allowed to use nouns anymore in transactions. Instead, you are allowed to use another field. What's your suggestion for this field? What we want this new field has the same application as nouns. Okay. I think the simplest answer is using timestamp. As you know, we use nouns to distinguish between the same transactions when all the fields like the sender, the receiver, the amount, fee are the same. Okay? If we cannot use nouns, we can simply use a timestamp instead. Okay? So the answer is using timestamp. And I solved all other questions. Next week is the last week before the final examination. Please review all the concepts. Then ask your questions. You can send your questions through the our group in Telegram. Then I will arrange all them, and I will have I will run another online session, and in that session I will answer all your questions. So next week is our last session. Okay. Please, all the persons who are already in this class, please put a sign here. Very good. Now, if you have any question, please let me know. If you have any question about all these concepts, about the these two midterm examinations, everything about the course. If you have any question, let me know. I will try to answer. Otherwise, you have one more week to review the concepts and ask your questions. Please, before the session, write your questions through the Telegram group. Then I can answer your questions faster. Okay?